The law of freely falling bodies states that all objects, regardless of their mass, have the same acceleration caused by gravity at a given location. This acceleration is constant, so no matter where the object is in its flight, the acceleration is always the same. And this can be demonstrated with a liquid accelerometer on an inclined plane, which I'll show you right now. The liquid accelerometer points in the direction of the acceleration. Now, I have this liquid accelerometer mounted on a cart, and what I'm doing right now is I'm zeroing it because I want to make sure that it indicates no acceleration when I'm holding it here on the inclined plane. So I'm using this, some putty. There we go. Alright, now when I release this, the gravity, okay, is going to cause it to accelerate down the inclined plane, and we should see the liquid orient itself in such a way that it forms like an arrow pointing in the direction of its acceleration. Watch. Did you see that? Let's take a look at it in slow motion. Now what I'm going to do is push the cart up the hill, and you should see that the cart is still accelerating down the incline because gravity is still causing it to accelerate down. Okay, watch. And I'll do that again. And again, just in case you missed it. Whoa! Try that again, it fell off the track. Okay, so I think you can just about see that when the liquid stops sloshing around, you get an arrow pointing that way, and that arrow starts pointing that way before it gets to the top. It stops, the arrow's still pointing that way, and then it goes down the hill, the arrow's still pointing that way. Let's take a look at this in slow motion. Now suppose I make this inclined plane steeper. Wouldn't you get the same results? Steeper still, wouldn't you get the same results? What about 89.9999999999999999999 degrees? Still get the same results. So the conclusion is that if it were 90 degrees, you get the same result. And this really shows that the acceleration due to gravity is always present, always acting in the same direction on whatever object is in free fall. Okay, and again, an inclined plane, what Galileo said was that an inclined plane can be thought of as a gravity diluter. So things on an inclined plane are sort of in free fall, but gravity is diluted. Now the law of freely falling bodies was actually tested on one of the Apollo moon missions. Let's take a look at that clip.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? That proves that Mr. Galileo was correct in his findings.
I'm sure that cost a lot of money, that experiment, a lot more than this. Okay, so let me go back to the board and continue with where I left off. Okay, suppose we wanted to construct a graph, the motion graphs, for a ball that's tossed into the air, like this. Now the story begins when the ball leaves my hand, and the story ends before it hits the ground or I catch it. So what I'm going to do here is first draw a diagram. Okay, so here is the ball when it leaves my hand. Okay, the ball reaches its highest point, and then it starts falling back. Let's say it passes my hand and falls to the floor, like that. Now I'm going to call this the 0 meter position. And now I'm going to construct a graph of position versus time, velocity versus time, and acceleration versus time. While I'm doing this, think about which graph would be the easiest to construct. Which one would be the easiest to sketch? I hope you determined this one to be the easiest, because it is. Remember, we have a constant downward acceleration. Okay, this is caused by gravity. Sometimes we use the symbol G, and we usually use 9.81 meters per second squared, or to make the calculation simpler, 10 meters per second squared can be used. Now down is usually the negative direction, so I'm just going to remind myself that up is positive. So on the acceleration versus time graph, when we just have a straight line parallel to the z-axis. The next easiest graph would be this one. The ball leaves my hand, it's traveling in the positive direction. So I'm going to start here. This will be my VO. When it reaches its highest point, the velocity is 0, and then it starts falling back down. So this is at the highest point, and right here would correspond to its velocity when it passes the point from which it was released. Okay, I'll just call that V1. And then down here would be the final velocity. Now the position versus time graph, to draw that, what I want to do is draw a dotted line right through the time when the ball is at its highest point, because the position versus time curve is a parabola, and I want it to flatten out at the top, right? Because the slope of a position versus time curve gives you the velocity, and the ball is at rest at the tippity top. There we go. So the slope here is 0. Here the slope is a maximum in the positive direction. Here the slope is a maximum in the negative direction. Okay, this would correspond to when it's located here. So the slope at this time should be V1. And then it continues falling to the ground. The area under a velocity time curve, recall, is the displacement. So if I found this area, here, you can almost see that it should be equal to 0, and it should be, because isn't the ball back where it started from? The slope of the velocity versus time curve is the acceleration, and you notice that it's a straight line, so it's a constant slope, which indicates a constant acceleration. And this value here, again, would be g, or about negative 9.8 meters per second squared.